Hi everybody, welcome to the last section in Math 1324. Section 8.5, Random Variables, Probability of Distribution and Expected Values. So, in here, first we need to define what is a random variable. But the focus on this is the expected values. Have a lot of the business implication. Right. But first, random variable. There are times when the interest is not in each simple event, but rather in some numerical values associated to the event. For example, if 3 coins are tossed, we might interest in the number of heads rather than a particular pattern. Definition: a random variable is a function that assigns numerical values to each simple event in the sample space S. So let's see how it works. Suppose that we are interested in the number of heads appear on each toss of 3 coins and the probability of the event. Let x be the number that indicates the number of heads in that experiment. Find probability of x. Right. So once again, let's write down. From the previous example, we did have the case where we have 3 coins. Let me write out again. Right. Or we can just write out again. So remember, you go like this: head, 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 and head. 4 head followed by 4 tail. The next one is going to be 2 head and 2 tail. Head, head, tail, tail, head, head, tail, tail. And the last one is alternating head and tail. Now we will construct the probability distribution. So for that we have x, the variable, will be the number of heads. Let's just tally. And then the probability of getting that particular event. So instead of having an event, we have the variable, which stands for some certain outcomes. Right. So for 3 let's just count. This have 3 heads, 2 heads, 2 heads, 1 head, 2 head, 1, 1, and 0. So how many 3 do we have? How many 0 do we have? 0. And there will be 1 out of 8. How many 1 head do we have? 1, 2, 3. So 3 out of 8. And there are 2 heads. 1, 2, 3 out of 8. And 3 heads, we only have 1 out of 8. So that is the random variable, which tells us how many heads we have and the probability of getting each case. So that is that together. Right. Next, the probability distribution of random variable x denotes this satisfy the sum of all the probability equal to 1. So if you add all of this up, it is equal to 1. And each one of this is between 0 and 1. So again, they have to add up to 1. And each one of them has to be between 0 and 1. So yes, so this one is a probability distribution. So expected values of a random variable. So expected values, if we have a probability distribution, so we have some variable, and then we have the probability. The expected values is equal to the sum of all the products. So pretty much we'll multiply this. So we just have the product of these two, x1 p1 and then x2 p2, and we add all of them up, we have what we call the expected values. Right, let's look at this. What is the expected values of the number of dots facing up on the roll of a single die? So the number of dots here is the random variable x. So that we may have 1 dot, 2 dot, 3 dot, 4, 5, or 6. So now those are not just events, those are values. It has values of a variable 1, 2, 3, 4, 5, 6, and this is a fair die, we assume. So the probability of that is 1 out of 6, 1 out of 6, 1 out of 6, 1 out of 6. Right. So again, the values is the number of dots. So you can say there's 6 outcomes, but this time not only we focus on the outcome, we focus on the values of the outcome. So, and that values have some significance. So now we just multiply straight across and add them. So x times p of x. So 1 times 1 over 6 is 1 over 6, 2 over 6, 3 over 6, 4 over 6. Of course you can simplify, but when you add them, add all of this up, you have 1 plus 2, 3, 4, 5, and 6. If you add all of this up, all of that over 6, and that gives us 21 over 6, which is 3.5. Right, so that means expected values is 3.5. So we say, wait a minute, how can we expect to roll dice and get 3.5 dots? Of course, you're not going to get 3.5. What we get expected values, meaning that if we flip or we toss that coin a very long time, for a very long time, over a very big number of time, then the average of all the dots is about 3.5. It makes sense, right? But 3.5 is between 1 and 6, so the average of 1 and 6, so that makes sense. So the expected values will not tell you what you get on one outcome. It will tell you that on average in the long run, what you expect to get on average of an outcome. So expect to get average about 3.5. Doesn't mean that you get 3.5, which you cannot. Right, so pretty much that. Right, and look at another example. A spinner is numbered from 0 to 5, and each of the 6 numbers is unlikely come up as any order. A player who bet $1 to any given number win $4. I mean, when they win $4, meaning, and get the $1 back. If the opponent come to rest and choose a number, otherwise $1 is lost. What is expected values of the game? So again, you have 0 to 5, and you can bet. If you bet $1 and you win 4, meaning you get $4, and then you also get back $1. In that case, what will be the outcome? What is expected values of the game? So there are 2 outcomes here. One is where we win and where we lose. And now the values. when we win $4. Meaning we get $4 back, and they give us back $1 as well. The $1 is what we bet. But if we lose, we're going to lose $1. We get nothing back. And then the probability of that. If you bet $1, if the opponent come to rest at the chosen number, so there's only 6 number, and you only have 1 out of 6 chance to win and 5 out of 6 chance to lose. Now multiply across. Take the values times the probability. You have 4 over 6 minus 5 over 6, and if you add them up, expected values is 4 over 6 plus negative 5 over 6 give you negative 1 over 6. So in the long run, we lose about 1 over 6 every time we play this game. Right. Just want to show you on the calculator real quick. On the calculator, when you hit stat, hit enter, it gives you the list of whatever it is. Never highlight it and hit delete, because if you do, you have to delete everything and name it again. Second 3 for L3, second 4 for L4, second 5 for L5, and second 6 for L6. So we have to rename again every single time. Right, so what we do is I'm going to do this one. So enter the numbers. The action on list 1, 2, 3, 4, 5, and 6. Good. Now for L2, enter that 1 divided by 6, 1 divided by 6, and so on. Right, so we have that, and then just hit mode, second mode. Now back to home screen. So we have list 1 and list 2. Right, now what we do is just take list 1 times list 2 and add all of them up, right? So hit stat, second stat, go to math, option number 5. So we're going to sum, we're going to add the product of list 1 times list 2. Of course, that's what we have. So again, second stat, and then go to math, option number 5. And now list 1, second one, list 2. Right, so we have that. Right, next. Look at this sample. A column had 20 laptop batteries, contain 2 defective ones. A random sample of 3 is selected from the 20 and tested. Let X be the random variable associated with the number of defective battery found in the sample. Find the probability distribution of X. So there are only 2 defective ones. There are 2 of them that are defective, and we select 3. So in that case, we may have 0 defective, 1 defective, or 2 defective. Now we will calculate the probability of F that X. Now if you have no defective and you select 3, so that means the first one is not defective, the second one is not, the third one is not. So the first one, there are 20 and 2 are defective, meaning 18 of them are good, have 20. And then the next one, when you have that out, you have 19 left, and 17 of them is still good. And then you have 16 left, have 18. So that is the probability of getting 0 defective. 20, 19, and 18. And with that, which convert to fraction 68 over 95. Right. Next, what is the probability of getting one that is defective? Right, now this a little more tricky. So one that is defective, right? We could have the first one that is defective and the second, the other two that are good. Or we could have the second one that is defective, the third one still good, and then the first two are good and the last one is defective. So we have those scenarios, so we have to add all three of them. Right. Now, to get one is defective, that two defective out of 20. And then next. The next one is not defective. There are 18 of them. I have 19. And there are 17. I have 18. Alright, next. There are 18 that are good out of 20. And there are 2 defective out of 19. And there's 17 good one out of 18. You see the bottom all the same, the top are all the same, so all of these 3 are the same. So pretty much we do one of them and multiply by 3. Right. Next, 18 of them that are good out of 20. 17 of them are good out of 19. And those 18 left, 2 are defective. And you see all 3 of them are the same. 20, 19, 18 at the bottom, and 2, 18, 17 on the top. So essentially, we just say 3 times. At the top, we have 2 times 18 times 17. And the bottom, 20, 19, and 18. Convert to fraction, we have 51 over 190. Because this is the probability distribution, you can just add those and subtract from 1. All of this have to add up to 1. But we're just going to do that again. Now defective one. Say 2 of them are defective. The other one is good. Now the first and the last one are defective. The middle one is good. And then the first one is good, but the last 2 are defective. Right, so there are 2 defective out of 20. The next will be 1 out of 19. And then how many good one? 18 good one out of 18. Right. Next, there are 2 out of 20. And there's 18 good one out of 19. And there's 1 defective out of 18. As you see, all 3 are the same again. 18 of them that are good out of 20. And then defective we have 2 out of 19 and 1 out of 18. So pretty much we have 3 of them. 2 times 1 Of course, 18 and 18 cancel out, so we just have that on the top and the bottom of 20 times 19. And we have that which converts to fraction 3 over 190. Right, so that is the probability distribution. Of course, you can add all of this up. 16 over 95 plus 51 over 190 plus 3 over 190. And you have 1, which is good. Right, find the expected values. My expected values is easy. Just multiply 3 across and then add them. This is just 3 numbers, so we can just say, just type it 0 times anything, well, that's still 0. We don't need to type that. This will be 0. That's silly. I'm just going to say it. 1 times 51 over 190, which is 51 over 190. We don't even need to times 1. Just I'm going to write that. And then 2 times 3 over 190. So this is the expected values, 0.3. So expected values is 0 times 68 over 95 plus 1 times 51 over 190 plus 2 times 3 over 190, and we have 0.3. So that means in the long run, if we select 3 of them, in the long run we have 0.30% of them. You expect to have 0.3 of them to be defective. Right, next let's go to this example. I suppose that you are interested in insuring a car video system for 2000 against theft. Insurance company charge for that for a premium for 1 year, claiming that empirical determined probability of 1.1, meaning 10%, that the system will be stolen sometime during the year. What is expected return from the insurance company if you take out this insurance? So if you buy insurance, so this is, let's say, most of the insurance have to be very clear about or whatever expected values, who with respect to who. So what is your expected return if you buy the insurance, right? So this is from your perspective. So you decide to buy the insurance. There are only 2 outcomes. One thing is it will not be stolen and you have no claim. So they have no claim, or meaning not stolen. And then we have a claim, which meaning that it is stolen. So those are the outcomes. And now the values. Because you pay the insurance regardless, you have to pay $225 out of your pocket. But if you are stolen and you make no claim, meaning that you're not going to get any more amount back. But if it is stolen, they will give you back 2,000, which give you 2,000 minus that 1,775. So those are the values, and this is negative 225. So 2,000 minus 225. Let's write that. Now the values are that, what you spend and what you get on each scenarios. Now the probability. What is expected value return if you okay, so probability claiming that 0.1 the system will be stolen. If 0.1 is stolen, this have to be subtracted from that. 1 subtract 0.1 is 0.9. So that's what we have. Therefore, the expected values is 0.9. I'm sorry, 0.9 times negative 225 plus 0.1 times that. So 0.9 times negative 225 plus 0.1 times 1775, that's negative 25. So that means you expect to lose 25. Of course, you're not going to lose 25. Either you're going to lose that much money, or you're going to gain that much. Not really a gain, but it's never, the value is not going to be negative 25. Either that much or that much. But in the long run, the company will make about $25 for each of those policies. So it's good, which is good. So if they have 1,000 of those policies, so each one of them will be $25. Yeah. Right. Let's look at this example. An outdoor concert featuring popular band is scheduled on Sunday afternoon in a large open stadium. The promoter is concerned about the rain out, and the long-range weather forecast predicts the chance of rain is at 0.24%. So 24% of that will be rain. If it does not rain, the promoter will gain 100,000. If it rains, the estimate net will be only 10,000. The insurance company will agree to insure the concert against the rain. For that, should the promoter buy the insurance? So in that case, we just find the expected values for each of the scenarios. So first, let's say if we decide to buy insurance, so with insurance, right. So again, there are only two outcomes: rain or not rain. And each time we find the values and the probability for each. So this is rain, outcome. There will be rain or no rain. Right. And then we have to determine the values. This is with insurance, right? So with insurance, that means you have to pay 20,000. Regardless of it's raining or not. But if it's no rain, you're going to net $100,000. So no rain, you have $100,000. Sorry. So that gives us 80,000. If there's no rain. But if it's rain, you still get $10,000. If it rain, you still get 10,000. But the insurance will pay also 100,000. So in that case, when it's rain, you're gonna get 90,000. So when no rain, you're going to get 80,000. But when it's rain, you get 90,000. And the probability raining, they set 0.24. Yeah, even though it ran, you still get 10,000. So when it not ran, of course, the complement 1 minus this, you have 0.76. Right, and now we have 90,000 with the probability of 0.24 plus 80,000 with the probability of 0.76, and to do that we have expected values of 82,400. So that with insurance. Now without insurance, construct similar table. Show outcomes. There rain and no rain. Probability of raining, not raining, and then the values. Okay, so you have the rain. This time you're not going to pay any insurance. So, but in that case, if it ran, you can only get 10,000. So that's the net values of 10,000. And if it's no rain, we get the full 100,000. And we multiply across, and that gives us the expected values. Multiply across and add them. So we have 10 times, so 10,000, sorry. Times 0.24 plus 100,000 times 0.76, and we have 78,400. Right, so we have those two, and of course you say it's clearly now with the insurance that we get the higher expected values, right? And of course it is, yes, but that is, I think in this case we should buy insurance not because of we have high expected values. Usually this would not be the case. The reason we should buy insurance because the values could only varies from 80,000 to 90,000. That is a lot more manageable compared to this 100,000 and 10,000. That completely different. So the insurance is not that, because we have to buy insurance, so the in real life expected values of this should be less than this. So the problem is there's something not right with the numbers. But the reason we buy insurance just so that the values will not change as significant, and that peace of mind. And then we don't have to worry about the extreme case when we lose. We didn't gain a lot of money in that case. So expected values wise, that's what we get. But we buy insurance not because of we got a high expected values. It's not going to be higher. Usually when we buy insurance, it's going to be negative expected value from us. But in that case, we'll not to prevent a significant loss. So when we buy insurance, we're losing something, but that prevents us from the significant loss. That's the idea of insurance. Right. With that, we finished everything I want to cover. Thank you for watching. Good luck on your final exam.